Hi, welcome to our next segment of Mathematics as a Second Language. And, I've always been a little bit annoyed at the speaker who says, before I begin speaking, there's something I'd like to say. But in our previous lesson, I left out a remark which didn't have much to do with the flow of what we were talking about, but I think it's interesting historically and pedagogically. You'll notice that the Semitic people invented place value working from right to left. In other words, the denominations increased in the right to left direction. Well, they also wrote in that direction. In other words, they kept place value going in the same direction as they ordinarily wrote. On the other hand, in Western civilization, we write from left to right, but we still do place value from right to left. And the reason was we borrowed the method from the Semitic people. All we knew was that it was a nice method and it worked really well. So as is often the case when you're doing something by memory, we just adopted it completely, no innovations. We didn't say, let's rearrange it so it goes in the order in which we write. We simply did it the way it was originally invented, which I think is kind of an interesting thing to point out, both in terms of teaching and in terms of historical note. The reason I bring it up in terms of teaching is this is a wonderful place to show students something that goes beyond math. Namely, that just because something is unnatural to you, unfamiliar to you, doesn't mean that it's unnatural. See, a lot of polarization stems from people saying that's not logical when what they really mean is, I've never seen it done that way. So for example, in class, when I write 642, I'll say to the students, now pretend this is place value going from left to right. What number is named by 642? Well, it would be 246. But many of the students say, that's not logical. You have to read it from left to right. And so we then get into a big discussion about this particular issue in which they learn some math, they learn some history, but they learn something that goes beyond the subject matter. I thought I would just mention that to you. And so the invention of place value wasn't in a vacuum. And so what happened was, let's see what goes into place value. Well, you have abstract symbols. Well, so did the Romans. The X didn't look like it stood for 10. The C didn't look like it stood for 100. You had to memorize that. Well, they said you traded in by tens. Well, so did the Romans. 10 I's was an X, 10 X's was a C. You say, yeah, but they had place value. Yeah, well, so did the sand reckoner. In other words, they didn't have different names. All the lines looked alike, but you could tell them apart by where they were positioned. In other words, you could see that the tens line was to the right of the hundreds line and to the left of the ones line, etc. So that was all there. What was really missing? In this final step of the evolution of place value, all that was missing was that up until now, the denominations were always visible. Whether it was an X, whether it was a line in the sand reckoner, they were visible. The Semitic people said, hey, instead of having stones on lines, let's invent names for numbers from anywhere up from 1 to 9. We'll invent numbers which we'll call digits. In fact, it's kind of interesting, again, historically, that the reason that we refer to our fingers and toes as digits was because that's originally started with the numbers 1 through 9 being called digits. So a single-digit number would be 4, a double-digit number two-digit number would be 24, etc. But what the Semitic people did is they invented these strange symbols, which I think we all recognize, 1, 2, 3, 4, 5, 6, 7, 8, 9, to stand for 1 tally mark, 2 tally marks, 3 tally marks, etc. Now, this of course looks very abstract, but remember that innovations seldom take place in a vacuum. That what happened was, yeah, these symbols are abstract, but how about the X, the C, and the M? They're abstract also. There's no way of looking at an X and telling that it stands for 10. You have to learn that. Well, you say, yeah, but the Romans traded in place value, you trade in by tens. Well, so did the Romans. Yeah, but in place value, you have position meaning something. In other words, what the adjective modified depend on where you placed it. Well, so did the sand reckoner. All that happened in place value, and it was a big change, was that for the first time, there was no visible symbol to tell you what number was being represented. For example, let me show you what I mean by that. On the abacus, the number 23 would be written this way. See, 2 on the ones column, 2 in the tens column, 3 in the ones column. You look at that and you can see why that's 23. Now, what happens on the abacus? Look at this number here. This is still 2 stones, but it's on the hundreds line. And this is still 3 stones, but it's on the ones line. Just by looking at this, you would say, oh, it's 2 hundreds and 3 ones. You wouldn't say, hey, I don't know how many tens we have. No, as long as the noun is visible, its absence tells us there are none of that denomination. For example, how would the Romans write 203? They would write C, C, I, and they wouldn't say, and no X's. Why would they say that? If the X's were there, you would have seen them. If there were stones on the tens line, you would have seen them. Same thing here. You look at this. This is what? 2 on the thousands line, 3 on the... This is 2,300, which the Romans would have written as MMCCC. No such... Not worried about, are there any tens or ones? What you see is what you get. This number would be read as what? But the Romans would write this as 2 M's and 3 I's. But now if we leave the nouns out, all we see is a sequence of digits 2 and 3. We know that we have 2 of a denomination and 3 of a denomination, but we don't know how many columns have been omitted. So what 0 was, it's not nothing. 0 is a placeholder. In other words, it's the 0 that tells us in place value that this number is 203. The symbol 0 by itself isn't important. What was important is that it was a placeholder. This says what? I have 3 in the ones column, none in the tens column, and 2 in the hundreds column. See, on the sand reckoner, if you wanted to indicate the number 3024, you would put 3 on the thousands line, 2 on the tens line, 4 on the ones line. So what happens is, when you're translating from the sand reckoner to Roman numerals, you put the digit that's represented by the stones underneath the appropriate line. In other words, I count 1, 2, 3. I put a 3 here. Nothing here, so I put the 0 as a placeholder. 2 stones here, so I put a 2 here. 4 stones here, so I put a 4 over here. And so this is basically how place value evolves. In other words, if I were to write something like this, it would tell me what? No ones, no tens, 300s, 2000s. And later on, if I wrote this, no ones, no tens, no hundreds, 3000s, 2 10,000s. And that's all there is to place value. In other words, the first big innovation is what? What made place value different from everything else was that there were no visible nouns. The column that the digit was in told you the noun, and to keep track of the missing column, 0 was used as a placeholder. Now, what you may have heard the expression, the more things change, the more they remain the same. As place value became more and more popular, you could write bigger and bigger numbers. In other words, you have his 5 ones, 7 tens, blah, 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 blah. Pretty soon, the number of digits becomes as overwhelming as it was way back when we were using tally marks, when it was difficult to tell the difference between, say, 17 tally marks and 19 tally marks just by looking at them. So what happened was we invented more shortcuts. Think of the word cat, for example. When you were a little kid, you sound it out, spell cat, because this is another idiosyncrasy of the English language. Spell cat, cat, C-A-T. I mean, cat should be spelled K-A-T if there was a logic to the English grammar. But we won't go into that right now. What happens is after a while, you don't look at the C, the A, and the T. You recognize this right away. Not only do you recognize it, but the chances are your mind conjures up a picture of a cat while you look at that word. So the same thing happens with, say, 642. You don't say I have 6 hundreds plus 4 tens plus 2 ones. It's pretty to recognize combinations of up to 3 digits, okay? So what they did next is if you had a number like this, 89456008993049875, what they did was they basically counted off in groups of 3 digits. And as we say, reading between the lines, what do you see here? 8, 945, 600, 893, 49, 875. But we don't have any names for these nouns yet. These were called the units, meaning whatever number this was, it was modifying a particular unit. It could be this many grains of sand, this many whatever, okay? So we had to invent new names. And so what we did was we essentially started trading in by thousands rather than by tens. In other words, using 3-digit combinations, the smallest number you would have is 000, and the biggest number you would have would be 999. Because once you got bigger than this, a new noun kicked in. So you never had to have more than 999 of any denomination, because as soon as you had 1,000 of one denomination, you could trade them in by one of the next denomination. And so what we did was, instead of using these lines, we used commas, and then we gave these names. See, the first group of 3 was called units, meaning you put in whatever you were describing, grains of sand, pencils, whatever. The next group of 3 were called thousands. The next group of 3 would be called millions. The next group, billions. And then it went on according to the prefixes tri, quad, quint, etc. See, billions, trillions, quadrillions, quintillions, etc. And notice again what happens over here. For example, if I put a 3 over here, the 3 is modifying tens. 3 tens is 30. The 30 is modifying millions, okay? If I put the 3 over here, the 3 is modifying hundreds, and the 300 is modifying billions. So it's a new vocabulary that we have to use, and it allows us to write numbers in an easier way to see. So for example, now rewriting that number, if I say to you, what is the 6 modifying? Well, where is the 6? In the sequence of digits, it's 100, so this number here is 600. What noun is the 600 modifying? Units, thousands, millions, billions. So you sort of get the idea? See, what's the 4 modifying here? Well, it's in the tens place, so it's 40. 40 what? Units, thousands, millions, billions, trillions. So this is what? Let's do it this way. This is units, thousands, millions, billions, trillions, quadrillions. And how would you read this? 8 quadrillion, 945 trillion, 600 billion, 893 million, 49,875 of whatever you were counting. And by the way, these numbers get big very fast. Way back in the late Middle Ages, I don't remember exactly the exact dates offhand. I should have looked it up before today's lesson. But again, if you're interested, you can look it up. Google is a wonderful invention now. You don't have to memorize facts. You just Google whatever you want to know. But there was a man named Avogadro who developed a very important chemical theory based on something called Avogadro's number. And that was the number of atoms in what they called a mole of a substance. So in terms of more familiar terms, it would be the number of atoms in about an ounce of water, a half ounce of water. And the number he came up with was a 6 followed by 23 zeros. I don't even know how you'd read this. Units, thousands, millions, billions, trillions, quadrillion, quintillion, sextrillion, 600 sextrillion. Pretty big number. And I'll tell you how big that number is. I mean, this you can tell by looking at this it's a big number, but you can still write it down pretty easy, couldn't you? If you could write a trillion, if you could count 1 trillion atoms per second, 1 trillion atoms per second, it would take more than 3 million years to count that many. Do you see the power? Can you visualize doing something that, now to give you an idea of how big a trillion is, if you were a multi-billionaire and you wanted to be philanthropic and you decided that you were going to give away $1,000 every second, 24/7, every second, in other words, every second of the day, every day of the year, all going on, if you gave away $1,000 every second without stopping, it would be 31 years before you gave away $1 trillion. That's the power of the nomenclature we have today. Can you see how this would be science fiction back in the days of tally marks? How things grew that way? Avogadro's number. I mean, that is poetic. I mean, think of what it means to be able to have a vision that says that many of atoms in a half an ounce of water. I mean, that's a poetic vision. In other words, mathematics isn't just the language of science. It's a liberal art. It's a humanities subject where you can relive all of the greatness of human achievement. But now I'm waxing on too much again, so let's come to our practice problem of the day. Okay? And this is something that I think kids have a lot of trouble with. A lot of people do, but here's the problem of the day. Represent the number below as a place value numeral. And the number is 20,185,000. Okay? Just to get an idea of how place value works. So pause the video, write down what you think the answer is, and then I'll show you how I did the problem. The trick in counting big numbers is you don't look at ones, tens, and hundreds anymore. Your new nouns are units, thousands, millions, billions, and trillions. So as I read this, what are the key words I see? Trillion. See, I skip over the 20. I skip over the 185. Next is stuff. So what's modifying trillions? 20. So I have 20 trillions. What's the next adjective? 185. But what's it modifying? It's modifying thousands. So this is trillions. So it says I have no billions. I have no millions. See, 20 trillions. No billions. No millions. 185,000. And that's it. Remember, I need these zeros in here. The zeros aren't nothing. If I leave these zeros out, what do I get? You say zero is nothing. No, there's a big difference between 20,185 and 20,185,000. And again, if you want to think of this a different way, the best way to show that zero isn't nothing is suppose you're buying house numerals at $10 a numeral, and you live at number 43. You have to pay $10 for the 4 and $10 for the 3. That's $20. What if you live at number 40? Do you say to the merchant, here's 10 for the 4 and 0 is nothing, so I'm not going to pay you for it? You pay for the digit 0 the same way as you would for the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. The only difference is, in the same way that 2 tells you you have this many of a denomination, 0 simply tells you you have none of the denomination. Okay? And I guess that wraps up today's lesson. I'm already looking forward to talking to you again next time, and I hope all of you have a great day. Take care.